Hi everyone, I'm very glad to stand here and present the OpenCAPI Acceleration Framework to you. Okay, so actually I believe a lot of people here had already heard CAPI Snap, which was the acceleration framework for CAPI 1.0 and 2.0. And it provides a quite convenient environment to port algorithms and computation to FPGA. And today I'm going to take OpenCAPI acceleration work here and introduce the details about it. Okay, so today my contents including the basic FPGA acceleration paradigms, the components and the workflow, and our testing result about the framework bandwidth and latency. You will be interested in that. And the last one is some examples to fully utilize OpenCAPI acceleration framework. So first, because you know Power 9 has emphasized its I/O capability to connect all of the computing components of FPGA and GPU. So today, the OpenCAPI is really a hot topic. And we will see that it makes the FPGA or ASIC accelerator to be placed to the parallel place like CPU cores. So you can call that FPGA accelerator as another heterogeneous processor. And I want to mention one point is that in last presentation, Dimitri had introduced the C1 mode and M1 mode. And here, I will say that the OpenCAPI acceleration framework actually focused on C1 mode. That means all of the transactions are initiated from the accelerator. So the FPGA side is the master. It will send the transaction commands with virtual address. And these commands will go through OpenCAPI links and arrive at on-chip coherent interconnection. Sometimes we call that nest. Okay, and after the virtual address arrived, so the power processor will look up the data in its cache subsystem. And so this is a coherent access. And sometimes, finally, it has to go to the external local memory. So that's the whole story of OpenCAPI stack for our acceleration framework. Okay. So today, I want to mention that for acceleration, we should focus from two aspects. The first one is to offload the CPU computation. So traditional, we execute all of the functions with CPU, with software. And when we move the computation to FPGA card, actually, we are utilized the capability of FPGA resources. That includes the combinational logic and also the memories and all kinds of things. You should pay attention to the instruction complexity. That means in one cycle, you can do a particular job with some complicated steps. So not like a CPU instruction. Actually, FPGA uses the gates and circuits to fulfill a function. And another important thing is to utilize the parallelism. That means you must equip multiple engines and finely tune the pipeline between the data dependency. So in that case, you can get the computation get accelerated on FPGA card. So this is the first paradigm. And the second one is to explore FPGA's I/O capabilities. That means we can move data ingress and outgress. So today, FPGA cards can be designed based on customer requests, and you can design any external interfaces as you want. So for example, you can have the interface. This is the NVMe connection to to the hard disk or the storage, and the below picture is the connection to Ethernet. So for different FPGA cards, you can have the different connections. That means if your source data is located in hard disk or in memory, you don't need to use additional hard disk driver or additional Ethernet card to move data to host first. You can directly use the FPGA to get the data and doing the computation and send the results and exchange the data with host CPU. All right, so let's look closer into the OpenCAPI Acceleration Framework. So first is, its abbreviation is OC-Accel. So from the left side, it is the software running on host server. So people can write software programs as they want, and actually a lot of people have done a lot of work to explore to upper levels. And we have OSNAP library, and this is a user space library and talks to liboc-accel. And later, lower, it is OC-Accel, it is a kernel module, and it has already been included in most of Linux distributions today. On the right side, it is the hardware FPGA part. So we have OpenCAPI to AXI bridge, which will convert the OpenCAPI TRX DRX to two interfaces. The first one is AXI 4 Lite. In this case, the hardware action, which is the logic part owned by the developers or by the users. This part is a slave. And the main data part is this here. It is an AXI 4 memory mapped interface. And here, the hardware action is a master, and it uses virtual address to access host memory. And you can also expand your connections to this FPGA card's external IOs. For example, we have DDR memory controller. We can also have NVMe controller here, and we have Ethernet controller here. So as you wish, and you can expand it. All right, so the next thing is about the OpenCAPI board support package. So if you have a new card, you want to design a specific card, and you want to claim that your card is supported in OpenCAPI Acceleration Framework, you can bring the details into this board support package. So today, it already supports Alpha Data 9v3 card, and quickly in our pipeline, we are going to support the Alpha Data 9H7 and the Bitware N250 SoC, and so on. You just need to provide the constraint files, some particular Verilog files for your top design, and also some specific IPs that you are going to use. All right, so this is the main workflow for OpenCAPI Acceleration Framework. So it is more like an integrated development environment, IDE. Okay, so we have optimized those steps to integrated in one Python script. It is called Snap Workflow. So after preparing the environment, you have two options to write the hardware part. So so you have to write the application running on CPU. You also have to design your acceleration on hardware. You have two options here. One is to write the Verilog design, and the other is to use HRS C++. So after both the software part and the hardware part are ready, we can do some code simulation. This is an important step to guarantee that your work can work correctly before you go to test it on real hardware. So basically, if you have passed the code simulation, you have solved 95% of correctness, or I should say functional logic. So the next thing is to build FPGA image. And in this step, you need to take care of the timing, the place, and the route. So after FPGA image is ready, you can deploy the application side and the image to Power9 server. Okay, so here I will spend several minutes to describe the options for the hardware development. So if you are a Verilog developer, we have improved AXI memory mapped master interface. So compared to the original Snap for CAPI 1.0 and 2.0, it supports new features. Okay, and it even has a protocol interface monitor on this port. So that means it can track your AXI transactions, check if they are complying with the protocol. So let's see the AXI features here. So first, the address, they are the same, 64 bits effective address. And for the data, the OC-Accel has increased from 512 bits to 1024. Okay, and for the bus size, that means the data bus size. So 1024 means 128 bytes. We support all kinds of narrow-sized transfers. I think that may benefit for the Apache Narrow or something. Okay, so we support all kinds from 1 byte. But previously, Snap only supports 64 bytes. That is the full size of data width. Okay, and burst length, we didn't change that. It is the same. And for the burst mode, we also added a fixed type. Okay, so we also support write strobe. We also support 5 bits of AXI IDs. That means 32 IDs. So that means if you have 32 engines, you don't need to change anything, and you can get the multiple engines working, and each one use a different ID. We also support multiple processes to access the FPGA hardware. So currently we support 5 and 12 pass IDs. That means process context. That's the number of process context. All right, so if you are a C++ HRS developer, so things are quite easy to start. So in this page, you just pay attention to this function. This is the entrance. It has 4 arguments, and the first one, din gmem, dout gmem, it's simply mapped to this master interface. Okay, so actually they just look like 2 data arrays. You can use your 64 bits virtual address to index the arrays. Okay, and this DDR mem mapped to this port. It can talk to the memory on card. And so action register, it is this slave port. It can get the the control information and the status information, and talked through the MMIO. Yeah, here. Okay, so yeah, this picture shows OCSE. So how do we run a software and hardware co-simulation? Actually, we will start at least 3 processes on our development environment. So the first one is to start the simulator. Currently, we support the Cadence simulator and also the built-in Vivado simulator. And OCSE, you look at it, it looks like a bridge. Actually, on the software side, it provides a OCSE version of liboc-accel and talk to software. And on the right side, it provides a Verilog AFU driver to directly drive the TRX to AFU interface. So for the as the second process, as the second process, it is OCSE, and the third process is your application. You can run your application anytime, just like running on real Power 9 hardware. And you can track the simulation result and make sure that the results are correct. Okay, so we also gather all of the documentation and the support message on a website, on a static website. It has the user guide part and also some examples and also some, if you want to learn more about this acceleration framework, you can go to this deep dive tab. All right, so here is the bandwidth result of today's OC-Accel. So you will see if you move data from host to FPGA, that means the FPGA reads data. Okay, the bandwidth is about 21.6 gigabytes per second. And if you move data from FPGA to host, that means FPGA writes something, and the bandwidth is similar. And if FPGA sends read and write requests at the same time, this is the duplex case, we can get both at about 18 gigabytes per second. So next is the latency. So we measure latency in this way. Here on the master port, it will send AXI commands. So we measure when we send the AXI address, and the AXI address actually will go this parse and to get the data for read, okay, and come back, and this is the read data. So from send read address to get read data on this, so we averagely need 495 nanoseconds. And for the writes, it is a little shorter at about 450. By the way, this latency number can be even shorter because currently our snap call runs at 200 megahertz. And it can, if we can enhance that to 300 or even 400, the latency number can be around 400 nanoseconds. Okay, so in the following pages, I will try to introduce some examples, especially for the developers, what we can consider to fully utilize this OpenCAPI Acceleration Framework. So the main idea comes from, actually that from CAPI 1.0, it has the idea of shared memory. So that means the software thread can set some work elements, and it can execute software tasks and track status and access any address at any time. And FPGA side, it gets the work elements and do hardware computation, and it can access any address at any time within the same context. Okay, so they are talking in the same context, process context. So the first idea is with OpenCAPI Acceleration Framework, actually you can try to accelerate more and smaller functions. Basically, we can do profiling. This is a part of the diagram we did profiling for H.265 video encoder. It is a very big diagram, and we can pick up, we can look at the numbers and find out the hotspot functions. And you can identify the input arguments and the output arguments, and use the acceleration framework to do some. So it doesn't have to be a very big function. Even some smaller functions, it can get accelerated. The second idea is about scattered memory access. Actually, we have already seen a lot of benefits from this side, this idea. So for a traditional PCIe-based FPGA acceleration, you need to have device driver, and you'd better to gather all of the data you need by software and to a data block. And then you ask the DMA to make a transaction of a big amount of data to FPGA. That is the most efficient way in this scenario. But with CAPI or OpenCAPI, we can just send the address or the list handler pointer. We just need a pointer to FPGA, and FPGA can read the scattered memory directly with the address. So today a lot of software, actually they have very completed data structures like lists or graphs. So the traditional DMA way actually is not very good at that, but CAPI and OpenCAPI can make that happen. So the third idea is asking software and hardware to working together. So in the left diagram, so in this case, FPGA just doing some offloading. So because we don't have a device driver running in the background, so in this case, the utilization of CPU is very, very low. It is usually 1 or 2% of CPU time. So CPU, at that time, it can be used to do other tasks. Or you can carefully design the software and hardware cooperation. So ask them to run in pipeline. So, and because our overhead is shorter, so you don't lose a lot of things during the interaction. Okay, and the first example is about moving data between GPU and FPGA. Everyone knows that Power 9 also has NVLink. And actually, today we are using GPU to do a lot of fancy computation, but in some cases, the GPU also needs some pre-processing and post-processing for example, for the video or for the images. And in this case, FPGA can work with GPU together. And the best thing is that they can share the unified memory. FPGA use OpenCAPI interface and the GPU use NVLink interface. It is very convenient, and we already have an example running in this way. So the fifth example is about the Ethernet acceleration. Because today we have a matched bandwidth. So for the Ethernet, if you use 1 Gbps Ethernet IP, it is exactly identical to the OpenCAPI bandwidth. All right, so what's more, next season, we are also working on LoadEMA. So this one is trying to help you port the existing PCIe-based accelerator to OpenCAPI. So it will provide the exactly same interface like Xilinx runtime and Xilinx XDMA. So actually it has a job manager here, and it will interpret the job descriptors and move data for you. So it provides two AXI Lite interfaces and several channels of AXI data ports, and it can either be memory mapped or stream-like. Okay, so that is all for my today's presentation, and you should try to fully utilize this OpenCAPI acceleration work with the global memory sharing and open and easy developing, and the good throughput, because today it is the biggest throughput in the world, and the latency. Okay, so yeah.
Good.
Any questions?
Hi, thank you for your talk. It's nice to see the developments. So I was wondering about your slide that showed the HLS interface for a snap action for OpenCAPI.
Yeah.
I saw there was a D-in and D-out parameter on the interface to access the host memory, right?
Yes.
So why do you have two parameters to interface with that AXI bus?
So if I understand your question correctly, it means, oh, I didn't prepare that chart, but you know, HRS can synthesize AXI4 interfaces. Okay, so you give it a directive and tell him that this port I want to AXI4 port, so it can synthesize that for you automatically. Yeah, and it provides a memory array model. So if you want to get data, you just say array index, I give you the index, and I get the data. If I want to store data, I just say memory index, and you can store the data.
So you have to have two ports because one port cannot be both read and write. So one's the output, one's input, that all you need to.
Yes.
There's limitation of the tooling. Okay.
But there was only one more DDR, right?
Yeah, exactly. You know, we didn't change that because for the CAPI 1.0 and 2.0, it is like that, because we want to keep the old actions developed on Snap still can work on OpenCAPI Acceleration Framework, so we didn't change that. Actually, we have some backup. I want to show you that is okay, but it does have a data width mismatch. You know, the original one is 5 and 12, so we will automatically insert an AXI DVIS converter to do the job. So you can, if you have some old Snap accelerators, you can move to the new one without any efforts. Hey.
I have a question regarding the integration of NVLink CAPI
Okay.
on the same memory. The only question I have probably to know the internals of the NVLink side. Are you able via the NVLink to coherently call for a schema function for the spin loss as we have from the CAPI?
Actually, today they use the data logs, and actually. Oh, so you are talking about AMO. We haven't implemented AMO, atomic, right?
So how you coordinate the access between the links at the public?
So actually, we have read flag and write flag. It acts like a status exchange. Yeah.
We use flags. So whenever the one has finished writing his section, the other one is informed that it can get the data, and there is two interleaving processes to make sure that we utilize the full balance. It's just an example that we are set up.
Yes, fine. So I don't know what we think that's what
Yes. So it's doing smooth that.
Thanks.
Okay.
On one slide, you had mentioned latency.
Okay.
Latency of the data. Just slide back to that. The question is, in terms of the data that you're reading, is that resident? Does it have to be resident in cache at those times?
Okay, so if you want to get the best latency, you should guarantee that the data is in the cache by initialize the allocated memory. Otherwise, yeah, it will take longer time. But that's not caused by the OpenCAPI, it is caused by the cache system here.
It's not significantly longer.
Mm-hmm.
The DRAM time is a little longer, but not significantly. So you're talking a low percentage of your overall. Yeah.
Hey.
Thank you for your talk. A few questions about the availability. When is it going to be public?
Sorry?
Is it already public or?
Well, actually, we are undergoing some legal review process, and I believe it will be open soon. Yeah. Yeah.
Any other questions? And thank the speaker again.